Right. Morning, guys. Hope you're all well. Welcome to another session of network architecture. And today we're going to be looking at the IPs, just specifically understanding exactly what's happening with IP version 4, looking at the different classes, assignment, and just understanding the mechanisms associated with that specific protocol. Now, last week we discussed the OSI model. And if you remember well, we had those 7 distinctive layers or stacks that all fed from each other to create a distinctive model that just enables you to understand specifically what's happening as far as peer-to-peer configuration is concerned, how packets or datagrams or frames are sent from source to destination, and ultimately what actually happens at the core level as far as network configuration there is concerned. So today, what we want to do is concentrate specifically on what's happening as far as the IPs that I mentioned a couple of seconds ago. And I think ultimately also looking at the generic relationship between the transport layer as well as the network layer. If you remember well, what we mentioned is that the transport layer's main purpose is just to look at availing obviously connectivity and looks at those distinctive protocols that we mentioned, the transmission control protocol that looks at guaranteed delivery. Why is the delivery guaranteed? Is because you get some kind of acknowledgement from the receiver as far as your generic connection is concerned. Ultimately, slightly slower, but obviously quite reliable. Why? Because you're guaranteed that the message is typically received. On the other hand, you've got the UDP or the user datagram protocol, and ultimately that one is a lot faster, but less reliable. Why? Because naturally you don't get some kind of acknowledgement as far as the actual receiver there is concerned. So it's also known as effortless delivery. Why? Because again, a network typically doesn't need to be established. It's assumed that the connectivity is there. It's assumed that whoever has been sent the message typically has gotten it. And on the other hand, that's the reason why we were mentioning that TCP deals with guaranteed delivery. Why? Because they've got that acknowledgement platform associated with your environment. On the other hand, with the network layer, remember the network layer we mentioned that specifically deals with routing. So on the other hand, what we're looking at in this particular instance now is that when you're looking at routing, you're mapping a pathway as far as sending and receiving is concerned. So technically, it's to do with efficiency, and in some instances, some might want to argue it also deals with security in some instances, where you're now defining specific pathways that are supposed to be taken as far as sending and receiving is concerned. So ultimately, you've got logical addresses that you're dealing with as far as the network layer is concerned. And obviously, what are these logical addresses? This is where the internet protocol comes into the foray there. So if I was to, let me see if I can quickly share the screen here. Hopefully, we can get something going. All right, so we want to see what's happening. We just want to understand, again, like I was saying earlier on, what are the actual mechanisms put in place? How does this particular protocol function? And obviously why it's relevant as far as unique assignment of addresses and identification on the network is concerned. So you've got the TCP IP platform. So TCP over IP is the same thing as transmission control protocol over the internet protocol there. And ultimately, what is happening as far as your specific setups they are concerned, remember, we've just mentioned that as far as TCP is concerned, or as far as the actual transport layer is concerned, you've got your transmission control protocol and you've got the user datagram protocol. So TCP, that's your transmission control protocol. You already know this. And as far as the IP is concerned, so that's your internet protocol. All right. And remember, like we mentioned before, as far as conventions they are concerned, you're looking at this from the network layer, sorry, the transport layer rather. Let's quickly fix that. So you're looking at this as the transport layer platform. So that's your transport layer. And then on the other hand, as far as the IP goes, you're now dealing with the network layer as far as conventions they are concerned. All right. So ultimately, designed all the way or configured all the way back, I think in 74, 76, if I'm not mistaken. And then the true protocol stacks were identified as lone entities. I think late 70s, 78 thereabouts. And from there, they've been identified as two distinctive entities. And ultimately, I think one of the specific advantages really the benefits of using these particular stacks is that they're not proprietary. So it's an open standard, can be used across the board. So whether you're using a Windows operating system or working with Windows network configurations, whether you're dealing with Linux, whether you're dealing with Mac, TCP/IP remains open. It's not proprietary. It doesn't belong to a specific a set of individuals or organizations, and makes it a lot easier as far as basic implementation within your network environments is concerned. So ultimately, if you look at for instance, the IP, all right, we mentioned this before, your IP is sitting with version 4, and you will also have version 6 incorporated there. The distinctive differences between the two is obviously the amount of addresses that can be configured or that can be gotten within specific environments. Remember, when you're looking at IP version 4, you're typically sitting with a 32-bit address. And as far as your 32-bit address is concerned, the total or the maximum that you've got is 2 to the power 32 there. And then you're sitting with about 4.2 billion IPs, all right, as an approximation. And then on the other hand, with IP version 6, it's a 128-bit address now. And as far as that is concerned, like we mentioned before, your total is roughly about 340 trillion IPs. All right, so you can see the massive jump. I think we've mentioned this before in our previous sessions there. So technically, the reason why obviously IP version 6 was designed is to accommodate for the discrepancies that were experienced with IP version 4, which is obviously limitations, because obviously when it was initially configured and designed, that amount that you see there was applicable, was appropriate, but obviously with the exponential growth of the internet space, ultimately there needed to be some other addressing scheme that could then accommodate for that growth, then accommodate for the massive number of IP addresses that were needed as far as basic connectivity is concerned. But ultimately, I think if you want to look at it from a different perspective, IP version 6's rather main issues is that IP version 6 is replacing or was typically designed to replace IP version 4 as opposed to upgrade IP version 4. So remember, there's a difference there from a technical point of view. If you're upgrading something, you've got a foundation to work on. If you're replacing, then that means you're coming with new or completely new architecture, completely new conventions or configurations dependent. So there's bound to be certain discrepancies, obviously, that you'd experience as far as generic usage there is concerned. But ultimately, they've worked on certain concepts that try and alleviate those discrepancies and try to make sure that there's some kind of congruence as far as functionality between these two versions as far as configurations are concerned. I think other literatures would want to mention that IP version 5 was typically used as a testing platform just to make sure that the actual upgrade there, or the actual change rather, or the actual movement can function appropriately without any distinctive glitches as far as configurations would go. But obviously, IP version 4 is still in use. You still need to understand how it actually functions, so that obviously when there is that move to IP version 6, there is a generic understanding of what's happening with the whole concept of the internet protocol, and obviously why it's relevant as far as conventions they are concerned. So ultimately, remember, it's the whole concept of unique identification as far as your distinctive spaces there is concerned. So remember, every IP, so as an argument, a typical example of an IP version 4 address would look something along these lines. So this is a typical example of what an IPv4 address would look like. So I've got 192.168.7, maybe .3. That's a typical example of what an IPv4 address would look like. And where the 32-bit convention comes into play there is that each individual portion, obviously, of those 4 numbers that I've plugged in on screen there would be represented by 8 binary digits. Remember, we use decimal as far as basic numbering systems are concerned. But on the other hand, your computer system obviously deals with binary or binary digits or bits, whichever way you look at it, combination of zeros and ones that obviously would then be represented in different formats as far as configurations would go. So those bits that I've just mentioned a couple of seconds ago would represent characters, letters, and generic numbers that you'd find as far as our everyday numbering or lettering system is concerned, whichever way you look at it. So like I was saying a couple of seconds ago, what this typically means is that you've got 32 bits representing 192. You've got 8 bits representing 192, another 8 bits representing 168, another 8 bits representing 7, and then obviously another 8 bits representing the number 3 there to give you a total of 32-bit configurations there. Which would then mean, if you were to look at it from a distinctive perspective, you've got a maximum and you've got a minimum associated with a representation there. So if you look at it from a binary point of view, remember binary is 1 and 0 or 0 and 1, whichever way you look at it. So you only have 2 numbering systems that are there or 2 numbers that you find there. And obviously the numbering system is base 2 not included because obviously it defines the numbering system. So remember, whenever you look at numbering systems, 0 is actually identified as a digit incorporated within that distinctive range there. So ultimately, what it means is, if you look at it from a binary point of view, your minimum number in that range is 0, and obviously your maximum number in that range is 1. On the other hand, if you look at decimal, it's 0 to 9, so obviously your minimum number is 0, your maximum number is 9, dependent. So technically, if you want to look at the maximums in terms of representation as far as the decimal to binary and vice versa is concerned, with an IPv4 address, what we're saying is, as an argument, we've mentioned the fact that 0 is your minimum number there. So ultimately, if you've got 8 zeros, so we've got 0, 1, 2, 3, 4, 5, 6, 7, and 8. That then obviously should equate to 0 in decimal. On the other hand, the maximum of the 8-bit configurations that you've got is obviously going to be 1, 2, 3, 4, 5, 6, 7, and 8. And obviously that equates to 255. So what this typically means is that in an IPv4 address, you can never have a number that is less than 0. And at the same time, you can never have a number that is greater than 255. And obviously, where is this numbering platform coming from? So if you look at the whole concept of binary, base 2. So you've got 2 to the power 7, 2 to the power 6, 2 to the power 5, 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 1, and then 2 to the power 0. Remember, 0 is incorporated there. So already we've got 8 distinctive positions associated with what we've incorporated on screen there. So technically, if you're looking at it from a different perspective, 2 to the power 7 is the same thing as writing 128. That is the same thing as writing 64. Remember, it's base 2, so it makes it a lot easier. So you either, if you're going from most significant to least significant, you're actually just dividing by 2. If you're going from least significant to most significant, all you're doing is just multiplying by 2 there. So 2 to the power 5 is going to be 32. That is 16. 2 cubed is 8. 2 squared is going to be 4. 2 to the power 1, remember, any number to the power 1 is that number, and 2 to the power 0, any number to the power 0 is 1. So ultimately, if you're looking at it from a generic point of view, remember we've mentioned electronics before. 0 represents an off state or insignificant state. A 1 represents an on state or a significant state. So if it's all zeros, then naturally it means that all these positions are distinctively irrelevant or non-significant, and that obviously equates to 0 as far as your decimal perspectives are concerned. But then if they're all ones, on the other hand, what it then means now is that you're adding 128 to 64 to 32 to 16 to 8 to 4 to 2 and then 1, and that would obviously give you 255. So this is where the mathematics comes into the foray there. That's the reason why you find that all ones give you 255, all zeros, on the other hand, give you a 0 as far as conventions would go. So on the other hand, if you look at the IP address, so any IP address will have a network portion, will have a node portion. So for instance, if I was to give you a very generic example as far as addresses are concerned. So if you look at an address, let's say we've got 35, let's say William and Nicole Avenue, and this is in Constantia. Let's say Constantia Kloof. This is in Rudiport. And obviously, this is in Johannesburg. Right. This is a typical example of an address. All right. And remember, as with every address, you've got distinctive portions. All right. And each one of those portions identify exactly what is happening as far as your environment is concerned. So if you look at what we've got on screen there, 35 represents the actual location or the actual house number as far as your environment was concerned. So we'll call this, let's call this the house number. And then Constantia Kloof, on the other hand, shows you the suburban area that you're in. So that's suburb. All right. So that's your suburb. And then Rudiport is your town. And then obviously Johannesburg is the actual city that you're in. So that's the breakdown as far as that particular address is concerned. Right? It's the same thing when you're looking at it from an IP perspective. As far as an IP address is concerned, you've got a specific portion that should identify the network that this particular gadget or device is in. And then at the same time, you've got the actual host portion, which then directly identifies the actual gadget itself. So remember, these gadgets we're talking about, or these devices we're talking about, can either be a router, can either be a switch, can either be an actual computer system or a server, whichever way you look at it. But obviously, anything that can be networked, anything that can ultimately send and receive is distinctively identified by that IP address. So if you look at what we initially had, whichever way you look at it, you've got 192.168, maybe .7.3. It means that that IP address has got a network portion, which identifies the network that that particular device is in, and it's got a host or node portion. So as a typical example, this sits in a specific class that's called Class C. We'll look at those classes in a moment. So from a superficial point of view, just by looking at that particular class, because you've got what they call subnet masks, which are also conventions that are used to identify which is the network portion, which is the node portion associated with your IP address. And this being a Class C address, again, like I said before, we will delve into that in a second. So this address sits in Class C. As far as Class C is concerned, you've got the first three portions there representing the actual network. All right, and then the last portion there actually representing what is called the host. All right, so it means that the first three portions of that IP version 4 Class C address identify the network that it's sitting in, and then the actual last part there would identify the direct machine, the direct gadget, or the direct device that is incorporated within your distinctive environment there. So I want to look at now the distinctive classes that are associated with IP version 4, in order for you to also understand specifically what is happening as far as assignment is concerned. How would you actually choose these IP addresses, and how are they actually used as far as your specific environments they are concerned. So if we go back here, so we're now looking at the different let's fix that quickly. All right, so you're now looking at the different classes IPs. So you've got class A all the way to class E there. So A starts at 1.0.0.0 all the way to 126.255.255.255. And then class B starts at 128.0.0.0 all the way to 191.255.255.255. And then class C starts at 192.0.0.0 all the way to 223.255.255.255. And then class D would start at 240.0.0.0 all the way to 239.255.255.255. And then obviously, lastly, we've got class E that starts at oopsie, I think I made a bit of a blunder here. This is supposed to be 224. Apologies there. So this IP is actually supposed to be 224. So this is 224. And then this is now 240.0.0.0 all the way to 255.255.255.255. So these are the IP address ranges associated with IP version 4. So these are the classes for obviously IPv4. All right, as far as generic usage there is concerned. So you've got a range of IP addresses. And obviously, again, like I was saying a couple of moments ago, usage would obviously be dependent on what do you actually need or how you're configuring your network as far as your setup is concerned. So ultimately, you've got those as the distinctive ranges. You've got the classes that are there. But again, your as far as these particular classes are concerned, classes D and E, unfortunately, cannot be used or not available for public use. Why? Because these particular ranges have been reserved for what they call multicasting, broadcasting, so multicasting, research, and experimentation. All right. So class, which technically means that you never be, or you typically won't use classes D and E. Why? Because those particular classes have distinctly been reserved for broadcasting, multicasting, ultimately research and experimentation. So you can see that the pool of IP addresses that is available for use has also shrunk as far as what you've got on screen there is concerned, which means that what is applicable is classes A, B, and C only as far as basic use there is concerned. So there's a need to further understand exactly, like I was saying, in which environments you'd use which classes and obviously why it's applicable in that distinctive environment there. And as you can see, if you look at classes B all the way to E as an argument, you'll discover that there is some kind of sequence in terms of what ends, obviously, the next then starts the distinctive range and so on. So we're ending at 191 in class B, starting at 192 in class C, ending at 223 in the same class, and then starting at 224 in class D, ending at 239 in the same class, and then naturally jumping to 240 for class E. But on the other hand, if you look at class A, we've got 127 that has not been incorporated there because we end at 126 for class A and then jump to 128 as far as class B is concerned. The reason is the 127 range has been distinctively reserved for troubleshooting purposes, So ultimately, you find that normally, if you want to check for connectivity, if you want to check for functionality at a basic level, as far as your network interface card is concerned, you'd use what is called the ping command. Remember, the ping command in your command line is used to test for connectivity. You type out ping, you put in a space, and then 127.0.0.1. That particular IP address is the IP address of every NIC on the planet. So technically, what you're doing is just to test for connectivity. Typically, you might find that you're having intermittent connectivity as far as your network interface card is concerned. At the same time, you probably will discover that you're having distinctive issues as far as generic connectivity is concerned. You want to check at a core level first to see if that particular network interface card is functioning appropriately. You use the ping command to do that. And obviously, the IP address that you need to incorporate is that IP address that is sitting within the 127 range. So it's specifically 127.0.0.1, but the entirety of the range has distinctively been reserved for troubleshooting purposes. That's the reason why you typically would not find it included. Yes, fair and fine, it will still form part and parcel of Class A, but as far as the actual assignment, when it comes to your hosts or your nodes or your gadgets or devices, that particular range has distinctively been reserved or excluded completely. So now ultimately, when you look at the classes again, like I was saying, each particular IP address will have a specific portion. You've got a network portion, and then you also find a distinctive host portion. Now, earlier on, I was just saying that you've got D and E that have been excluded. So ultimately, you now have only A, B, and C. And to look at a better assignment of these IPs, or to more or less extend the range, if you want to look at it from a different point of view, private addressing schemes were designed. So in each class, class A, B, and C, you've got a private address range that is normally used within internal networks or your local area network configurations. And then you'd use what is called, because these particular private addresses are not routable, which means that you cannot connect to an external network when you've got your machine configured with a private address. So ultimately, to accommodate for connectivity, a specific architecture that is called NAT or NAT or Network Address Translation was initially designed to translate or to convert those internal addressing schemes or those private addresses to external configurations or external networks or external IPs to avail for connectivity to the external network conventions there. So before we look at how NAT actually functions, let's look at the different private IP addresses that are associated with your IP version 4. So you've got private address ranges, so private IPs. And as far as these private IPs are concerned, Class A would have 10.0.0.0 all the way to 10.255. And then Class B would sit with 172.16.0.0 all the way to 172.31.255.255. And then lastly, I think a lot of gamers would be familiar with this range, 192.168.0.0 all the way to 192.168.255.255. So these are your private address ranges in each one of these classes, all right? And ultimately, like I said before, these particular IP addresses or these particular ranges are non-routable, which means that you cannot connect to an external network using these particular IPs. So private IPs are non-routable. So all that means, like we said before, is just that you can't connect to an external network if you've got your gadget or you've got your device configured with an IP version 4 private address range. So how does this actually take place? So you've got NAT. We'll look at obviously subdivision of network and node portions later. But you've got what they call NAT, which is short for Network Address Translation. Like I said before, this is an architecture that has been designed specifically to enable devices to connect or devices or private addressing schemes to connect to the external network. So it's a way of masking internal addressing schemes. At the same time, it's a way of looking at translating, or even you can even argue from a security point of view as well. So look at how Nat functions in a diagrammatic format from a basic point of view. So let's say we're sitting with 3 machines there. Obviously, a lot more can be configured. We've got our switch, we've got our router, and then let's say we've got connectivity to the internet. All right, so technically, so what we've got there is we've got a switch, and then we've got a router. So as far as computer system 1, 2, and 3 is concerned, let's assume we're sitting with IPs that are sitting within the private address range of class A. So let's go 10.0.0.17, for instance. And then for the second one, probably 10.0.0.23. For the last one here, 10.0.0, maybe .8. And then our switch is sitting at 10.0.0, probably .3. Our router is also sitting at 10.0. Maybe let's say .1. All right, so these are private addresses, as you can see. All right, but these private addresses, we just mentioned that they're not routable, but we've got connectivity to the net. And like we said before, you've got network address translation architecture that has been configured into your router to enable that a router to mask any IPs that are sitting behind it, or any gadgets that are sitting behind it from the external network, which is obviously going to be the internet. And remember, it's not just the internet, but it can be any external network that you've got. So public IP addresses are the ones that are routable, right? Private are the ones that are not. So when NAT rather, or network address translation is configured, you've got your router technically sitting with 2 IPs, one public and one private. Private for the internal addressing platform, and then public for connectivity to the external network. So as an argument, you are sitting with possibly, let's say, public IP, let's just say 156.31.17.3 as an argument. All right, so that's a public IP. All right, that's the one that enables now connectivity of this internal network to the internet. On the other hand, now, if the internet space or the external network is trying to communicate with or trying to access the internal, all they see is this particular IP. All right, so the external network will see the one single public IP that is incorporated there, while behind that particular public IP, you've got a multitude of computer systems that are sitting there. So it presents brilliant security to a certain extent, and at the same time, it presents better management of IP addresses, because you can imagine a scenario where you're sitting with 100 machines, or even the setup that we've got on campus. Each one of those machines in the computer room, I think you're typically sitting with about 20 odd calculation's sake, you're sitting with 20 odd machines in each one of the computer rooms that are on campus. You're sitting with about 6 odd computer rooms. That means we're looking at 120 machines. All those computer systems obviously need connectivity to the net. So ultimately, if we don't have NAT incorporated, what it typically means is that you need to actually have 100, or you need to buy 120 public IP addresses for connectivity to the internet. That doesn't make any economic sense. And at the same time, it also doesn't make any configurative sense when it comes to your own network design. So to look at a better management of those IPs, you can buy one IP address and then one public IP address, and that one public IP address can avail for connectivity to the internet for a multitude of computer systems, just using your network address translation platform as far as configurative conventions they are concerned. So that's how NAT functions, and obviously that's how those private addressing schemes that I was mentioning a couple of seconds ago would then connect to the external network as far as your computer systems are concerned. Now, on the other hand, if you look at what we were mentioning in terms of the IPs having or in terms of the whole concept of an IP address having distinctive portions, you've got an architecture called a subnet mask. So you've got a default subnet mask. Now remember, a subnet is or subnetting or subnets are all different portions of a network. So subnetting is subdividing a network into smaller portions or into different portions or into a multitude of portions, obviously for better management, better for IP assignment and so on. So you've got an architecture called a subnet mask that is used to then identify which is the network portion of a class A IP address, which is a network portion of a class B IP address, what is the node portion or what is the host portion of that same address as far as conventions would go. So each one of these classes, so with class A, you've got a default subnet mask of 255.0.0.0. With class B, you've got 255.255.0.0. And then lastly, with class C, you've got 255.255.255.0. So from a superficial point of view, what this actually means is that if you're sitting with a class A address, the first portion of that address is representing the network. The last three portions are representing the actual host associated with your machine mechanisms. Same difference would go with class B. First two portions there would be your network. Last two portions would be host. And then if you're sitting with a class a C address, the first three portions would be representing the network, and the last would be representing the host. So obviously, subnet mask would use an architecture called binary ANDing to arguably represent or look at what the network portion is, and at the same time use the same architecture to represent what the host or node portion is. So if you were to look at it from this point of view, just for argument's sake, generically speaking, what it actually means is that if you remember, you've got 255 just being represented by 8 ones. You've got 0 represented by 8 zeros, just as an argument. So if you look at it from a different point of view, what this actually means, although we'll delve into that deeper in the next couple of slides there. If you're looking at class, remember, IP version 4, 32 bits. So the first portion there is 8 bits, right? The last three portions for class A would be obviously 24 bits. All right. Same difference if you're looking at it from class B's point of view. The first two there would be 8 plus 8, 16. The last two, 8 plus 8 again, another 16 to give you 32. And then if you're looking at class C, the first three portions, 24 bits. And then the last portion is 8 bits to represent your actual host configurations there. So it means that from a generic point of view here, we are looking at 8 bits for network. And we're looking at 24 for your host. And then here you're looking at 16 bits rather. Let's just use some uniformity there. For network, and then you've got another 16 bits for host. And then here you've got 24 bits for network. And then you've got 8 rather. Math escapes me there. And then you got 8 for host. But it's not really as simple as that, all right? But obviously, this just gives you an idea, just to see exactly what's happening. But it's not as simple as that, because there's certain things that you obviously need to now take into consideration to understand now what are the actual bits associated with the network when you look at class A. What are the actual bits associated with the a host when you're looking at class A? Same difference applies for class B and C. So if you look at if you look at it from this point of view now, let's look at class A. All right, so let's look at class A. And if you remember well, we said that class A starts at 1.0.0.0, and it goes all the way to 126.255.255.255, like that. And as class A is concerned, remember our default mask, we said is 255.0.0.0. So let's keep that in mind. And technically what we've mentioned is that it's 8 bits for the network, 24 bits for the host. But now, if you look at binary representation now, using those 8 bits that we were mentioning earlier on, as far as your environment is concerned, we're looking at a scenario where, as far as our range is concerned, our range starts at 1, which means that our minimum for our range is 1, right? And at the same time, our range ends at 126, right? Which means that our maximum is 126, right? Are we all on the same page on that one? What it then now means is that if we were to represent these in binary, what does it actually show? So remember, with our binary conventions, just for argument's sake, we had 128, we had 64, we had 32, we had 16, we had 8, 4, 2, and ultimately 1. Right? So that's 2 to the power 0 all the way to 2 to the power 7. It's the same thing as far as representation is concerned. So what do we do if we want to represent 1 in binary? Right? So we look at the range of numbers that we've got. Right? As far as this range of numbers is concerned, what is the closest number to 1 that we've got there? We actually do have a 1. So ultimately, what it then means is that if you want to represent 1 there, we just we actually have a 1 incorporated there, and then everything else is a 0 because everything else is insignificant, right? Or everything else is off as far as conventions would go. So that would be 0, 0, 0, 0, 0, 0, and 0. So that equates to our 1, right? We want to now look at 126. How do we find 126? Or how do we represent 126 using the 8 bits that we've got as far as our conventions would go? Do we have a number that is close to 126 there? Yes, we have that number. It's actually 64. Remember, we can't talk about 128 because 128 is actually larger than 126. So the closest number that we've got to 126 in the list that we've got there is going to be 64. All right. And then if you look at it from a mathematics point of view, if we subtract our if you subtract 64 rather from 126, what do we get there? Let me see what we got. All right, so 126 minus 64 gives us 62. All right, what is the closest number that we've got as far as the range that we've got there is concerned? The closest number to 62 that we've got is actually 32. We subtract 32 from 62, we get 30. What's the closest number to 30 that we've got? Is 16. We subtract 16 from 30, we get 14. What's the closest number to 14 we've got? Is 8. Subtract 8 from 14 there, we get a 6. What's the closest number to 6? We've got a 4. We subtract 4 from 6 there, we get a 2. Closest number to 2, we actually have a 2, and then we've got representation incorporated in that distinctive fashion, which means that portion is a 0, that portion is a 0, and that equates to 126 in binary using our 8 bits. All right. So if you look at those two numbers, representation of 1, representation of 126. So remember, 1 is our minimum, 126 is our maximum as far as the range is concerned. But if you look at the range of numbers that we've got, there's one specific number that doesn't change. All right. So if you look at it from a different point of view here, 0 changes to 1 there. 0 changes to 1, that changes to that, that changes to that, that changes to that, that changes to that, that changes to that. But these two numbers, they don't change. So it means that when we're looking at an IP version for Class A address, what that actually means for us is that as far as conventions are concerned, instead of having 8 bits that represent our network portion, we are now left with 7 of them, because the first number there doesn't change. So we've got 7 bits that represent the actual a network itself. So what it then means is that we've got 7 bits for the network, for our network, which actually then means we've got 2 to the power 7, which is actually equal to 128 networks that we can get as far as Class A is concerned. All right. What it also then means is that if you've got 128 networks, what are we left with as far as our bit configurations are concerned? Remember, we've got one that has been excluded because it never changes. We've got plus the 7 that we've got incorporated, which means we've got 8. So if we subtract those 8 bits from 32, we are left with how many bits? We're left with 24. So as far as still sticking with class A there, what it now means is that as far as class A is concerned, we're left with 24 bits for our host. So this is 24 bits rather for our host, which then obviously equates to 2 to the power 24, which then gives us a number associated with that, which is ultimately 16,777,216. But remember, as far as IP addresses is concerned, you can never have all zeros or all ones, because when you're looking at it from a different perspective, all just to give you an idea there, let's just go back here. If you look at all zeros, it means that you've got 0.0.0.0, which actually equates to nothing. It's not an assignment at all, because remember, this actually equates to 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Another 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. So that's in binary. It doesn't equate to anything. And then you can also not have all ones. All right, because all ones would be 255.255.255.255, and then ultimately, remember, this is the same. It's the same as a broadcasting address, and it's also incorporated in Class E, which is arguably not usable as far as your environments would go. So there will be 2 IP addresses that you won't use in any given IP address range. So ultimately, what it then means is that this particular number now goes from 16,777,216. Now, because of the 2 that we can't use, all right, minus the 2, it means that the total number of hosts that we can get for Class A would then become 16,777,214. All right, so that's for Class A. So it means that anytime we're looking at Class A, the maximum number of networks that we can get is 128 networks. Some literatures might want to say 127 because you also have that convention incorporated, but it's actually 128 networks that you've got incorporated there. And then ultimately, you will also have a maximum of 16,777,214 hosts that you can get as far as Class A is concerned. It's the same when you look at Class B now. If you look at Class B, remember Class B, we've got our default mask of 255.255.0.0. All right, that will obviously mean that the first 2 portions represent network, the last 2 represent host. But if you want to look at it again, like we said before, it's not really as simple as that. You obviously have to take content into consideration. Class B would actually start at, where does our Class B start at? It starts at 128.0.0 all the way to 191.255.255.255. All right. Again, if you want to look at it from a different point of view, we want to look at a representation of 128. We want to also look at a representation of 191 as far as your conventions they are concerned. So if you remember, if you look at our list initially, 128 is 1, 2, 3, 4, 5, 6, 7, and 8. And remember how we got that. You still have your 128, you still have your 64, you still have your 32, you still have your 16, you still have your 8, you still have your 4, you still have your 2, and you still have your 1. So here, obviously, closest number to 128, we actually have a 128, so we're good to go. But when you're looking at representation of 191 now, on the other hand, remember 191, what's our closest number as far as 191 is concerned? We've got 128. We subtract 128 from 191, we get a 63. What's our closest number to 63 there? It's actually 32. We subtract 32 from 63 there, because that's our remainder. We've got 31, so we've got a 16 there. We subtract 16 from 31. What do we get? We get a 15. And what's the closest number to 15 there? We've got an 8. 15 minus 8, we get a 7. Closest number to 7, we get a 4. 4 from 7, we get 3. Closest number to 3, we get a 2. 3 minus 2, we get a 1. Closest number to 1, we actually have a 1. So our representation there will be that. So if you look at our numbers again, 128 and 191 in binary, which numbers never change as far as that is concerned. Our first 2 digits there, as you can see, our first 2 digits typically stay the same. So now what it means as far as clause B is concerned, instead of having those 16 bits, which is your 8 plus 8 there, we actually have 16 minus 2, because we've got those 2 bits that never change. So we now have 14 bits that represent the network. All right, so 14 bits, that's your network. And that equates to 2 to the power 14. What does that give us as far as totals are concerned? You're getting 16,384 networks, right? So when you're looking at class B, the maximum number of networks you can get is obviously 16,384. On the other hand, now the remaining, so you see here, we've got 2 bits here. So we've got the 2 bits that, let me see if I can put this in a different ink there. So we've got the 2 bits, all right, that we remove initially, but it stays the same. So these are your leading bits. And then from those 2 bits, we are left with 14. Because initially we had 16 bits that were representing the network portion that is there, all right? And then what does it mean as far as the remainder is concerned? We're still remaining with 16 bits there. So what it typically then means is that as far as our actual host is concerned, we've got 2 to the power 16, all right, which gives you 65,536. But remember, we've got those 2 IPs. So you've got the 2 IPs that you'll never use, all right? That will then mean that we now have 65,534 hosts that can be gotten. So 2 IPs that are typically removed, or the 2 IPs that are say not used, and we just saw why. So with class B, what it typically then means is that you're now sitting with 65,534 as far as the hosts are concerned. And then if you look at class C, on the other hand, remember class C, we said that the default mask is 255.255.255.0. And as far as class C is concerned, class C starts at 192.0.0.0. Oopsie, that last needs to be moved. All right, and then that's going all the way to 253.255.255. So if you look at what we've got initially, so with class A, you've got 1 bit incorporated there as far as removing from the basic default is concerned. With class B, you've got 2 bits that have been removed. Obviously, with class C, it's the 3 bits that we're looking at as far as conventions would go. So again, same thing applies. You look at ultimately you will look at the binary representation. Oopsie, what happened with my, just chose the wrong pen there. So obviously you look at representation of that in binary, representation of that in binary. And like I said before, your three leading bits are then incorporated as far as basic representations they are concerned. So instead of having the initial 24-bit representation there as far as your networks is concerned, you've got the 24 minus the 3, which means that you've got 21. So as far as our 21 is concerned, 21 bits for the network. All right, and then obviously that's 2 to the power 21, and then obviously the total number of networks that we can get there is approximately 2,097,100 and should be 154 if I'm not mistaken. Let's just quickly confirm that. Give me 2 seconds. So we've got 2 to the power 21. Oh, it's actually 200 and it's actually 100 and come on, 52. So 152. That's the total number of networks that we can get as far as IP version 4 Class C is concerned, which would then mean what is remaining as far as our network bits they are concerned, or our host bits is concerned. That will then give us 8, the bits that are representing the host. So we've got now 2 to the power 8, which is equals to 256. But remember, you always have that 2 that we're talking about. So minus the 2, which will then give you the 254 hosts that can be gotten as far as your Class C platforms they are concerned. So that's how you typically look at the different classes associated with conventions there. I think one of the other things that you might also want to look at is remember, this is when you're dealing with classes. So you've got something that is typically defined to say, okay, look, if I'm looking at the Class A address, I'm going to go with obviously with a Class A default subnet mask. That would then enable me to identify which portion of that particular address is the network, which portion is the actual host or gadget or device that I've got in my environment. But remember, you can sit with what they call classless interdomain routing. So technically what this means is that you're not now restricted to using the distinctive default mask, because you can now typically customize your subnet mask to accommodate for more network portions as an argument, or to accommodate for more host portions dependent. But more often than not, you're looking at accommodation of more network portions within your distinctive environment there. So as an argument, if you look at let's look at if you look at classes A default mask. So class A default mask is 255.0.0.0. And if you were to represent this in binary, remember this would then be 1, 2, 3, 4, 5, 6, 7, 8. And then that would be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And another 1, 2, 3, 4, 5, 6, 7, and 8. All right. So what it means is I've got 8 network portions there. All right, but remember, I can actually increase the number of networks that I've got. So I can't max out this portion. It's already maxed out. I've got 8 ones that are there, and I've got my maximum number that is there. So the next portion of the IP address, or next portion rather of mask that I can play around with, is going to be this distinctive portion there. And remember, you're always going to start at the most significant bit as opposed to the least significant bit, because then that would, if you started the least significant, that would then jeopardize the actual configuration, because you haven't incorporated the numbering platforms appropriately. So we continue from the last one that we've got, So technically, we can say, okay, look, as far as the next 8 bits is concerned, let's panel beat or change the first 3 bits to obviously, remember that's going to change to a 1 because with binary you only have a 0 and a 1. So technically, what we do then mean now is that we're sitting with 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, and then the next one would be then 1, 2, 3. 4, 5, 6, 7, 8, and obviously the rest would be zeros there. So our new subnet mask would now be 255.128 plus 64 plus 32, which gives us 224.0.0. All right, so this is now our customized subnet mask that we can now change to say, okay, look, instead of having the first portion there as our network address, we now have 11 distinctive portions to represent the actual network, and obviously the remainder representing, which is another 21 that is now representing the network as far as your conventions would go. So what it would then mean now is that once you've customized this, these portions would represent your network, and obviously the last 21 would then represent the actual host. So this is when you customize. So this is also known as variable length subnet mask, and you can also even discuss the whole concept of what they call a CIDR, which is classless interdomain routing. And if you look at basic CIDR notation, so if you look at CIDR notation there, we can have an IP address probably that is, let's have an IP address probably that is sitting within the 127 range. Oh, that's sitting, sorry, within the class B range. So we can have maybe 139.111.87.3, and then we go /24 as an argument. So this is what CIDR notation is. All right, the /24 now, this particular number that we've got incorporated, this particular 24 represents the network portion of your, or represents the subnet mask. So in essence, what you can look at, this particular 24 represents your subnet mask. All right, so remember, if you look at this particular address, that's class B, but if you're looking at 24 bits that are representing the network, or 24 ones, if you're looking at it from a different perspective, that translates to the default mask for class C. Because remember, we're looking at 24 bits there. So what that then would mean is that the actual subnet mask associated with this IP address is going to be 255, which is 8 ones, plus another 255, which is another 8, which is 16, plus another 8, which is 24. So our actual subnet mask for this particular IP address would then be that. So this is the what they call classless interdomain routing, something that is just used to look at panel beating your own network. So you want to look at maybe expanding the number of private addresses that you can use. Ultimately, you can typically work with that convention as far as your specific environments there is concerned. So the other thing that you also want to discuss and also want to look at is assignment of these IP addresses. But before I do that, let me just, so let's just say, let's look at assignment of IPs. Assignment of IP addresses. And remember, this assignment can either be manual or it can be automated, so automatic. So this is also going to be assisting you as far as the whole issue of your particular project or your POE is concerned. So in essence, when you look at it from a different perspective, when you manually assign an IP, you're going to go and typically incorporate the actual IP address on your own as far as the actual machines they are concerned. All right. So if you're sitting with 5 machines, it's easy for you to do that because it's simple. You go from one machine, you incorporate your IP, you go to the next one. It's you're less prone to errors in such an environment because you're only sitting with 5 computer systems. So it's easy for you to remember that, okay, the last one that I incorporated was 192.168.0.17. So the next one is going to be 18, the next one is going to be 19, the next is going to be 20, and then the next one is going to be 21. Easy for you to incorporate. But imagine if you are sitting with 100 machines and you actually have to manually go from one computer system to the other. It's obviously going to be a bit problematic because you're prone to human error. I mean, it's all natural. So to avoid that kind of discrepancy, and remember, not just human error. Let's assume that you're perfect at your numbering. You've done it accordingly as far as 100 machines is concerned. The time that it takes for you to move, to incorporate, to sit at the computer system, open up your IP config setup, incorporate your IP address, move to the next one, and so on and so on and so on. It takes a lot of time because remember, you're a human being at the end of the day. So ultimately, you're going to be less efficient in such an environment. So you might need an actual platform that can automate that process to say that, okay, look, I'm sitting with a specific range of IPs that are from this particular start point to this particular end point, and I want to have these automated as far as assignment is concerned, as far as my 100 machines would go. So with automatic assignment, what you're actually dealing with is what they call the Dhcp protocol, all right? And or the Dhcp platform. And remember, Dhcp stands for Dynamic Host Configuration Protocol. So Dhcp is, that's Dynamic Host Configuration protocol. And the main purpose of this is to automatically assign IP addresses within any given environment. So you normally have Dhcp architectures configured into routers. You also have roles associated with your servers. So when you install your server, you can actually activate and add the Dhcp role, which would then mean that your server is responsible for automatically dishing out IP addresses in any given environment from obviously a specific range that you will typically define. So the range associated with your Dhcp is actually known as a scope. So the Dhcp scope is ultimately the range associated. So from whatever start point to whatever end point, that's what your Dhcp scope is. And obviously the multitude of scopes that you can have, or the multitude of ranges that you can obviously be configured within your Dhcp server environment that then would then say, okay, look, I've got the first scope or the first range for this particular set of machines. I've got the second scope or the second range for this particular set of machines, and this will go on and on. I think this is also part and parcel of what you might need to incorporate as far as your assessment is concerned. But again, we'll have a practical session actually to show specifically how you'd go about that as far as assignment is concerned. So what I wanted to actually do is to show you what's happening with let me see if I can just stop sharing this for the time being and then move on to your command line. Hopefully we can have that incorporated. So remember, we've talked about the IP config space. So ipconfig /all gives you that as a result. And then what we've got the IP version 4 address. And as you can see, I'm sitting with an IP version 4 class C private address. But obviously you've got NAT incorporated that then obviously enables connectivity to the net. And then we've talked about the gateway before, which is your router. Technically, that's obviously the one that is associated with connectivity to the external network. But again, remember, you've got that router also sitting with a public IP that then would enable connectivity to your distinctive space. So for instance, if I was to assume, let's see, so the ping command, maybe let's go with the ping command first. Remember, we said the ping command is used for connectivity. Let's see if we can scroll this up a bit. And if I'm going to go 127.0.0.1, ultimately what I'm doing is pinging my network interface card. So ultimately, I want to check if that network interface card is working without issues. If I get 100% replies and 0% loss in terms of the packets that I've been, remember, there's a dummy packet that is normally sent just to test connectivity there, it means that my NIC is working without distinctive glitches. So I've got that as a response. And ultimately, the results that I've got there, as you can see, I've got 0% loss there. So ultimately, it means that my network interface card working without distinctive glitches. But obviously, if there are any other discrepancies, you might want to delve in deeper in terms of the troubleshoot process there. But now, I think what I was trying to put across now is the 127 range, distinctively reserved for research and not for research and experimentation, rather, but for troubleshooting purposes. So you find that yes, it's still part and parcel of class A. But ultimately, it's not used for assignment as far as your particular networking devices is concerned, because, like I said before, distinctively reserved for troubleshooting purposes. So if we go up again, DHCP there, as you can see, it's enabled, which means that the actual router that I'm using is automatically assigned these IPs as far as environments are concerned. I think what I want you to concentrate on as far as this particular IP there is concerned is that we've got 192.168.0.102, right? So that's a private IP address configuration there. So let's just go back. So 168.0.102. So let's just go back here. Let me see if I can stop sharing that. And then go back to our PowerPoint presentation. And then I think, yeah, so the IP address that this machine is sitting with is 192.168.0.106, right? If you remember. So what it means now, let's, let me see if I can go to the internet space there. Where's my browser? And then connect there and then show you exactly what I mean. All right, so let's let me see if I can share my browser here. Where's our browser? Okay, there. So we're gonna go, what is my IP? So remember, we had I was sitting with the 192.168.0.106, which is a private addressing scheme. And remember, we said that private addresses cannot typically be used for connectivity. Okay, they're non-routable. You can't use them to connect to external networks. But we got NAT configured, and that is what my public IP address is. That obviously then enables connectivity to the net there. So 155.158.221. That's the public IP address that I'm actually using from my ISP that then enables connectivity as far as the internet space there is concerned. So that's how typically NAT distinctively functions. That obviously avails for, like I was saying earlier on, better assignment of IPs, especially within the IP version 4 range there, and to some extent provides for a distinctive some semblance of security as far as your specific environments they are concerned. So in essence, I think what I would want you to do as far as let me see if we can look at a different section there. I think the last thing that we were discussing there was the DHCP, how that actually functions. So in essence, in 2 seconds here, just check my material. All right, so let's see if we can go back to our presentation. Okay, so this we can do without. So let's see if we can just minimize or rather erase that. Okay, it's happening there. Okay, no, that's fine. Then I think what we can do. Okay. See that if this can work then. Super. All right. So I was just mentioning the fact that when you look at DHCP, automatic assignment of your IP addresses, obviously works perfectly when you're looking at it from a larger type of network, and you've got a distinctive process, right, as far as your DHCP platform is concerned. So you've got specific messages, obviously, that are sent between the actual server and the machines that have got have been incorporated. And the first one there is the DHCP discover. So you've got the discover message or packets that are sent. And what's actually happening there is this message is actually sent by the actual client to try and start the actual lease associated with your IP address that is typically going to be given by a DHCP server. Remember, when you're granted an IP address, you're actually given a lease or a time frame that you can use that IP address as far as your configuration is concerned. So it can either be configured for an hour, can either be configured for 8 hours, can either be configured for a much longer period, dependent on configurations and environments that you're in. I think most of you. It's unfortunate now, but maybe later on, should we be able to pop into campus, if you run the IP config setup, you might discover that the IP address that you're given when you walk in, you're normally given about 8 odd hours, because it's expected, obviously, by if you walk in at 8, it's expected that probably by 4 or 5 or 6 p.m. you're out of campus. So obviously the lease that you've been given, or the IP address that you've been given, as far as your particular gadget is concerned, is expires after a specific time frame. You come in again tomorrow, same difference applies, you're granted an IP and so on. So as far as the discovery platform is concerned, this is actually a message that is sent by the client to start the IP address distinctive lease. And then the second thing that you're looking at is what is called the DHCP offer. And what is happening there is this is now a message that is returned by the DHCP server, obviously offering the distinctive computer system or distinctive gadget or distinctive network device that is being given an actual a valid IP address, obviously, and the lease to the actual requesting client. But obviously, I think in this particular instance, it's more applicable for us to be looking at it from a computer system point of view, because you don't want your networking devices like your routers and your switches to get their IPs from the DHCP server, because that can jeopardize network configuration. So normally your networking devices and your servers in certain instances are sitting with what they call static IP addresses, ones that are actually incorporated on the system itself, and those don't change as far as usage is concerned. When DHCP is enabled, it means that your IP addresses can change and you're getting automatic assignment from the DHCP server. But when it's static, it means that you've actually configured it on your distinctive machine there. And then the third one is the request. And then as far as the actual requests they are concerned, what you're looking at now is that it's now a message. So this is just like a handshaking process between client and server, or between machine and the actual DHCP server. So in this instance, this is an actual message now that is sent by the client to now state, or typically to indicate to the server that it's accepting that distinctive lease. And obviously, at the same time, to inform all the other servers that are there that their particular servers have been, or their particular offers have been declined. So it's a message now that is confirming that it's accepted at this particular IP address and lease from a distinctive server. If there's any other DHCP server within the environment, then ultimately those particular servers would get a message now that would state that they've declined, or the client has declined offer. And then lastly, you've got some kind of acknowledgement now. Acknowledgement. Right, so when you say acknowledge, so what's happening there now is that when the message now that has been sent by the server to acknowledge the client's acceptance of the actual IP address configuration there. So this is how your generic DHCP server platform actually functions as far as distinctive environments they are concerned. I think from a research point of view, let's let's mention this. So with research, look at manual. Manual IP address assignment. You can also look at DNS. All right, how does that actually function as far as your specific environments there are concerned? And then also look at common utilities. Utilities used in networking. And we've already used one of them, which is the ping command. Look at the other common ones that are used across platforms. So ones you'd find in Windows. I think the only other major change that you'll typically find really is when you're dealing with Linux-based machines, where you find instead of using ipconfig, you use ifconfig. As far as conventions they are concerned. So look at the other utilities that are in use as far as your configuration platforms they are concerned. I think what we will then want to do is when it comes to our next session, I think we want to discuss then how to access or more or less delve into the research that you'd have found, and then look at a practical session that then starts reiterating the whole concept of what's happening as far as how to create your client, how to create your servers, and so on. And I think the other thing that is also relevant is to understand the actual for instance, cabling and networking devices, how these actually function, because like I said before, remember you'll have a certain portion associated with your assessment that will need you to create or make your straight through cable as far as part and parcel of your submission there is concerned. But I think ultimately, from an IP address point of view, we should be good to go. So we will obviously then look at what you found as far as basic research there is concerned, and then probably just superficially look at IPv6, but just to understand how it just to understand the actual difference in terms of representation. And do we actually have classes in IP version 6? Do we actually deal with subnetting in IP version 6? If not, why? If so, why? Same difference applies. So probably look at that distinctive content as well, as far as conventions would go. So I think, as far as understanding the whole concept of IPs and whatnot, we should be good to go there. Understanding the classes, understanding assignment, understanding the whole concept of the distinctive network portions, host portions associated with your IP setup there. Do we have any pertinent questions, contributions from the floor there as far as today's session is concerned? I think if you want to look at added material, you can also go through chapter 7 as far as your prescribed text is concerned. But do we have any questions or contributions from the floor there?
Sir.
Yes, so what's happening?
So do you know when we can come back to college?
Unfortunately, I'm not clued on that. I think there should be some comms that will be sent out to you should need be. I think as of today we're under level 2 now, so I guess there's some certain restrictions that have been eased. But to the best of my knowledge, I'm not yet clued on what's happening on that one. If I do get any comms, I'll obviously communicate accordingly. But I am certain that I think the campus or the college itself would give you a heads up in terms of what's going to happen from here on out, and then we'll take it from there.
Okay, thank you, sir.
Not a problem. All right. Any other questions, Calvin? Are you still experiencing issues? I think today I'd given myself a self deadline to address your issue, but can you just give me are you still having issues across the board? Is it just with this particular module, or is it everyone else when you connect?
It's all of them where I just can't use the chat or see the chat.
And you're logging in with your student number, you said, right?
I am using my student number, the
your
student email.
Email, yes, exactly. Okay, so what I'll do is maybe as soon as I conclude this session, I'll just have a quick chat with your PM, just to see what's happening there. I think maybe just it could be an issue in terms of the way in which they would have configured your particular profile. So I'll just let them know that you can't send any form of chats associated, because when I see it on chats here, it shows outside the organization. So it means that probably you're not part and parcel of the actual team itself. So I'll give you a shout probably later on today to state what conclusions would have been gotten there.
Okay, cool. Thank you.
No problem.
Sir?
Yes, Kidus.
So I also had this problem where I couldn't see the chats and everything. All you need to do is come through Teams and not through the email.
Oh, is it through Teams as opposed to the email?
Problem.
All
yeah,
right, so
just don't use the email and then come through Teams.
Go through Teams. All right. So Calvin, have you been logging in through your email also, or have you been using the link that I sent, or are you logging in through your Teams platform?
I open Teams and go to the calendar, and then I click the events and say join.
Okay, so probably that also could be an issue. But let me see what's happening there, and then let me know. I'm not so sure if you heard what Kid has mentioned there, but probably in your next session, probably try and not just this one, but even for the other modules, try and log in the way that he would have mentioned. But if you're still experiencing the same issues, obviously there needs to be some kind of redress on that. But definitely today I'll get some kind of feedback from you from your PM, and I'll give you a shout.
Okay, cool. Thank you.
All right, cool beans. Do we have anyone else with questions, concerns, or contributions as far as today's session is concerned? There.
Sir.
Yes. What's happening?
So my assignments and stuff, I don't know if you've done marking them, but I didn't get my feedback or anything.
Is it?
Yeah.
Okay, I'll also look into that as well. I think marks should have been sent already to campus, so we'll find out what's happening. You did submit before the due date, right?
Yes, I did.
And through Teams as well, not through VCLAN.
I did both.
Okay, no, then that's fine. Okay, cool. I'll look into that and also give you a shout. If you don't hear from me again, as usual, please just pop me a mail and then we'll see what we can do.
Okay, no problem. Thanks, sir.
All right, cool beans. All right, do we have any other questions, guys, or contributions from the floor there? Questions or contributions, anyone? Questions or contributions?
No, sir.
Okay, cool. Not a problem then. If you're good to go, then that works. So again, look through content. I'll save obviously the slides and then post them on Learn. Again, this particular clip is being recorded, so ultimately I'll post that on YouTube as well. Should you need to go through it again, and then look through the research. So that I think today is our only session this week, if I'm not mistaken. The next time I see you, which is possibly sometime next week, we'll then cover that content and then obviously address any other issues that you might have there. But otherwise, if we don't have any questions, contributions, or concerns, then might as well call it a day. Stay safe and keep smiling. Remember, I think we're down to level 2 now. Don't get carried away. So just be vigilant as usual. So see you in the next one, guys. Cheers.
Thanks, sir.
Cheers, sir.
Cheers. Thank you, sir.
Thank you, sir.